Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
1904 Ludwig Boltzmann. The kinetic theory of gas stands as a testament to Boltzmann's enduring commitment to the microscopic underpinnings of macroscopic phenomena. This pivotal work, deeply rooted in the intellectual ferment of the early 20th century, meticulously explored the theoretical underpinnings of gaseous behavior, offering a profound insight into the atomistic nature of Boltzmann's meticulous analysis. Built upon the foundational work of earlier scientists, particularly Maxwell. He grappled with the conceptual challenge of using statistical methods to explain the observed properties of gases. Instead of meticulously tracing the intricate trajectories of individual molecules, Boltzmann sought to employ probabilistic frameworks to capture the collective behavior of an immense multitude of gas particles. This revolutionary approach allowed a precise description of the macroscopic properties of gases like pressure and temperature, derived directly from the average kinetic energies of these microscopic components. The work itself meticulously detailed the fundamental assumptions underpinning the kinetic theory. Central to this edifice was the postulate of continuous, random motion of particles. Boltzmann meticulously described the distribution of velocities among these particles, showcasing the importance of the Maxwell-Boltzmann distribution. This distribution quantifies the probabilities of different particle velocities within the gas at a given temperature. He systematically demonstrated how this distribution, derived from probabilistic considerations, directly correlated with experimentally observed phenomena. Boltzmann's work introduced a fundamental equation describing the evolution of the probability distribution of velocities in time, providing a framework for understanding collisions and energy exchanges among the particles. This 1904 treatise exhibited direct application in various fields. The kinetic theory powerfully explained the behavior of ideal gases. Calculations of pressure, diffusion coefficients, viscosity, and thermal conductivity could now be performed using the framework Boltzmann established. Furthermore, the work directly influenced the growing field of thermodynamics, enriching the understanding of heat transfer and associated phenomena. Boltzmann's approach facilitated the integration of statistical mechanics into the expanding arsenal of scientific tools. This powerful paradigm shift moved away from deterministic accounts of individual particle trajectories to statistical descriptions of collective ensembles. This approach proved immensely successful in addressing complex phenomena, where calculations of individual particle behaviors became computationally intractable. Boltzmann's theoretical work provided a potent tool for tackling issues in numerous scientific disciplines, establishing its impact far beyond the confines of the specific topic of gas dynamics. The work faced critical scrutiny, but, strikingly, many criticisms highlighted gaps in the prevailing understanding that Boltzmann's work helped address. Critics questioned the inherent assumptions underlying statistical mechanics. Boltzmann's work actively engaged and responded to these criticisms, further solidifying the robustness of his approach. The work stimulated much debate and further inquiry, pushing the bounds of scientific thought. Several key figures undeniably influenced Boltzmann's thinking on the topic. Maxwell's previous contributions were crucial, setting the stage for the statistical approach. The mathematical works of renowned probabilists of that time were also of substantial influence. Importantly, specific philosophical underpinnings of that era contributed directly to the theoretical foundations of Boltzmann's work. This complex network of influences created a fertile intellectual environment that shaped Boltzmann's path toward this particular exploration of the microscopic world. Boltzmann's 1904 work, in turn, directly influenced a multitude of subsequent developments. The conceptual framework laid out by Boltzmann became fundamental in establishing the foundations of statistical mechanics, providing a robust language for describing complex systems. The implications of Boltzmann's work reached well beyond gas theory. The influence extended to molecular dynamics, condensed matter physics, and many subsequent, disparate areas of scientific inquiry. The legacy of Boltzmann's 1904 work is evident in countless research endeavors, solidifying its enduring impact on scientific thought. Boltzmann's 1904 work on the kinetic theory of gases, therefore, stands as a monument to scientific progress. It epitomized a significant transition from deterministic to probabilistic explanations in physics, marking a turning point in the study of complex systems. By employing statistical methods, Boltzmann painted a detailed picture of a hidden world composed of continually colliding particles, and precisely quantified its influence on the macroscopic properties of gases. This work, a masterpiece of scientific insight, continues to serve as an inspiration both for scientists and historians of science.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.